This computer. Continue, cancel, stop video, share content, whiteboard. All right, welcome back. So where we left off in part one of this lecture, we discussed the strain energy of different cycloalkanes, and we said that cyclohexane had 0 strain, okay? What we're gonna do now is unpack this term strain energy a little bit, okay? So the question is, what am I actually talking about when I say strain energy? And so strain energy is derives from 3 specific factors. So the first is what we call angle strain. Okay, and this is destabilization that derives from deviations from ideal bond angles. And so for saturated hydrocarbons that are tetrahedral, it's always 109.5. So okay. The second contributor is what we call torsional strain. And we've already seen torsional strain when we talked about conformers of acyclic alkanes. So when you have 2 CH bonds eclipsing one another, that non-bonded destabilization is torsional strain. Okay, so destabilization arising from eclipsing interactions. And then the third contributor is what we call transannular strain. And this is a new one. And so transannular strain describes repulsive interactions between substituents across a ring. And for us, this is going to be involve sort of interactions between hydrogen atoms across a ring, okay? So Okay, and so I'll explain, give you an example when we get to the boat conformation of cyclohexane. Okay, so we can sort of identify these strain factors in different rings, and I'll, as an example, I'll do cyclopropane. Okay, so because cyclopropane only has 3 carbons, it's forced to be planar. There's nothing you can do to make it bend out of plane. So the molecule is flat. The hydrogens on each carbon are pointing above and below the plane of the board. Okay, and we can consider the bond angles in the ring. So these angles, of course, are going to be 60 degrees. And so we have quite a bit of angle strain. Normally, of course, we would want 109.5. So okay. The other important destabilizing factor in cyclohex or cyclopropane are going to be the CH eclipsing interactions, the torsional strain. And so all of the CH bonds, there are six eclipsing interactions within cyclopropane. So between here and here, here and here, here and here, and then the 3 sets of hydrogens in the back. And so each of those, if you think about ethane, we say that each eclipsing interaction is worth about a kcal. We get about 6 kcals from the eclipsing interactions in cyclopropane. So and so the net result of this is that there's a significant amount of strain in cyclopropane. It's about 29 kcals per mole of total strain. Okay. And this leads to some interesting chemistry of cyclopropane, undergoes ring opening reactions, essentially any pathway that can relieve that strain. 29 kcals is quite significant. Remember, like a CC pi bond is 58 kcals. So we're essentially half of the strength of a pi bond, which is not insignificant. And so anything the molecule can do to relieve that by ring opening, it will. But where we're going to spend most of our time on, because it's the most important, is cyclohexane itself. So let me draw that on the next page here. And so, to a first approximation, you might imagine that cyclohexane is going to be planar. Okay. And there's a real problem with this conformation, which is that the bond angles in this hypothetical planar geometry are 120 degrees. Okay, and we have 12 CH eclipsing interactions. So okay. So we would expect if cyclohexane were perfectly flat, there'd be quite a bit of destabilization relative to a straight chain alkane. And we know from our experimental heats of formation that that's not the case. The molecule is as stable as a straight chain alkane. So what's going on? And what happens is that cyclohexane adopts a non-planar geometry, which we refer to as a chair conformation. And that conformation has zero strain, okay? So what I'm going to do is we're going to spend a minute here explaining how to draw a chair and where the locations of the hydrogens are appropriately placed in that chair, okay? And so I can do this quickly because I've done this 1,000 times. That is a chair. That is the chair conformation of cyclohexane. Let me explain to you how to do it, how to draw it slowly. So the first thing you want to do is draw two parallel lines slightly offset from one another. And then we're going to draw a line going up and a line going down. And those two are going to be parallel to each other. And then finally, we connect everything. So, okay. So that is how I get to my chair. And so the key point is that the pairs of lines here are parallel to each other, okay? And so that's cyclohexane, but of course, each of those carbons is a CH2 group. There are two hydrogens attached to each carbon. And so we need to pencil this in. And this is what gives students the most trouble, I think, because up until this point, when we've drawn a carbon with its substituents with stereochemistry, we use the line wedge notation. And here we don't really do that because the three-dimensionality is sort of implicit in the chair backbone. And so you want to be careful when you want to practice drawing in the hydrogen. So I'm going to draw two diagrams. I'm going to put in one set of hydrogens and then the second in separate diagrams to make it hopefully clear, and then we'll combine them, okay? So the first thing I'm going to do is redraw my chair, okay? And I'm going to put in what we call the axial hydrogens. And so the axial hydrogens are the ones that are oriented vertically up and down. Okay. And in the second structure, I'm going to put in what we call the equatorial hydrogens. And these hydrogens are oriented more closely in towards the plane of the ring. And so we go like that and like that. Okay. And then finally, I can put it all together and show cyclohexane with all 12 CH bonds drawn explicitly. And it looks like that. Okay. And so again, so just to emphasize it, the equatorial hydrogens, I'll circle in red here. And the axial hydrogens, I'll circle in blue. Okay. And so it's important to get the approximate location of these hydrogens correct. And one way that might be helpful to think about this is to think of each carbon center as a inverted umbrella. All right. So let me draw that on the next slide here. I'll redraw the cyclohexane. Okay, so there's my cyclohexane with all its axial and equatorial protons. Now, if we just kind of like zero in on this carbon here, okay, and say, all right, I've sort of got a substituent coming out like this, one over here, one over here. If you imagine, that axial CH bond is the handle of an umbrella, and then it's kind of blown open. Blown open and flipped over. That is sort of where you want to orient everything when you're drawing this. So I've got an umbrella sort of upside down like that. If I were to do the one in the front, the umbrella would be facing the other way. So something like that. Okay. And so you want to adopt that approximate geometry. Why do I want to adopt that approximate geometry? Because in fact, each of those carbons is tetrahedral, right? And if I were going to translate this to a line wedge, it would look like that, sort of just as we would expect. We don't use the line wedge when we draw the cyclohexane because it would look very complicated, and the ring structure, the chair structure, implies to us the three-dimensionality of the molecule. Okay, and so so the chair conformation of cyclohexane has no strain energy. It's the most stable conformation of the molecule, and we can appreciate why it's so stable by generating what I like to call the double-barreled Newman projection. Okay, and so the double-barreled Newman projection is used for cyclohexane. You can use it for other rings. But what we're going to do, let me clean this up and make this all black again. What we're going to do in the double-barreled Newman projection is look down 2 carbon-carbon bonds at the same time, okay? And we're going to sort of ask the question, you know, what are the orientation of the substituents, okay? And so taking the ring as I've drawn it, we're not gonna, you know, we just kind of tilt it up. We're gonna look right down those bonds. And so I'm gonna start by drawing my carbons in the front. And I've got axial hydrogens coming down. So that's nice because that helps to orient me. So I have 2 CH bonds going down vertically. And then remember, when I make these Newman projections, you know, the apparent bond angles are 120 degrees because I'm looking down a bond. So I have a line here and a line here, okay? And then I can do the same thing on the other side. A line there and a line there. I connect the 2 in the center. Let me number the carbons. That'll probably be helpful. So 1, 2, 3, 1, 2, 3, okay? And let's call these HX, HX, HEQ, HEQ. And so this is HX, HX, HEQ, HEQ, okay? And so it looks, you know, it looks complicated, but this is essentially just the front end of 2 Newman projections connected to each other. And then, as with any normal Newman projection, I draw the back carbon as a circle, okay? And so that carbon, those circles correspond to C4 and C6. And so I'll just put a little, I'll put a little 4 there and a 6 there, okay? And then I have to figure out where the substituents go. And if you look at C4, I have a hydrogen going up, my axial hydrogen. I also have that at C6. And so I can draw those in just like that. Those are HX, HX. And then the 2 equatorial protons attached at those positions are coming down like this. Okay. And so these 2 right here and here are the equatorial protons attached to C4 and C6. And then I just need to connect with C5, and that is coming down like that, okay? So this is just a fancy Newman projection, but it's cool because what it shows us is that all of the substituents are staggered, right? All of the adjacent CH bonds are perfectly staggered, just like in our old friend ethane. Okay, so this is a much more complicated context, but the logic is the same. We always take staggered conformation as being the lowest energy conformation, 0 strain, 0 torsional strain. And here in cyclohexane, I can achieve that when I make a chair. Okay, and so what I've shown it here, the double-barreled Newman projection, looking down C1, C6, C3, C4. But you should convince yourself that it looks identical if you go C5, C6, C3, C2. You get to the same type of double-barreled Newman projection. Everything in the chair of cyclohexane is perfectly staggered. Okay, and that is why there's zero strain energy. All right. So I want to just introduce two more conformers of cyclohexane before we finish up. And the first is what we call the boat conformer. And the boat conformer looks something like this. Okay, so it's essentially a chair, but I've taken one end of that chair, say the bottom one, and flipped it all the way up. Okay. In this drawing, I've omitted the hydrogens from the back just so it doesn't get too busy. Okay. This conformer is about 7 kcals higher in energy than a chair. Okay. And there are two contributors to that increase in energy. The first is a transannular interaction. So the two H's that are pointing in here are bumping into one another. Okay. And that is an example of a transannular interaction. So across the ring, two substituents, two hydrogens bumping into each other. This type of interaction, because cyclohexane is so prevalent and boat cyclohexane comes up a lot, we give this a special name. This is known as a flagpole interaction. Okay. And then the second contributor to that 7 kcals per mole are the CH eclipsing interactions. So there are 4 CH eclipsing interactions. Okay, and those are between pairs of CH bonds on either side of the ring. So, okay, and so this conformer is 7 kcals is a lot in terms of energy. There's almost no boat conformer present in solution. It's non-zero, but it's very small. Okay, and it's the highest energy conformer of cyclohexane. All right. The other one that's important, which will come into play when we talk about chair flips, is what we call the twist boat. And the twist boat is actually a little bit tricky to see and to conceptualize, but it's as if you take this boat conformer and sort of twist the apical carbons. And so you end up with something like this. Okay, and so this is a really great spot to use models, build the chair, flip it to the boat, and then make the twist boat from that. Okay, the twist boat is slightly more stable than the bona fide boat conformation. So this is only about 5.5 kcals per mole higher in energy than a chair. Okay. And the main reason is that while there's still a flagpole interaction, it's diminished somewhat because those hydrogens are a bit further from each other than they are in a boat. So okay, and so it's slightly more stable. Okay, so I'm going to sort of titrate in the conformers of cyclohexane. There's half chair, which we also need to talk about, but we'll save that for the next lecture when we get into chair flips. For right now, if you're watching this before the weekend, what I'd really encourage you to do is practice drawing chairs, practice getting the axial and equatorial hydrogens in the right places. Like draw a chair 1,000 times over the weekend. Like it'll help. Um, if you have models, hopefully you do. If not, find a friend that does. Convert the chair into a boat and then to a twist boat, and become comfortable with those different conformers, because we're going to use them in the next lecture when we start doing what we call chair flips, which is flipping those chair conformers around. All right, so that concludes lecture 19.